What's up, young noobs? In this video, we are going to learn how to not camp in Call of Duty and how to find pH of weak acids and bases. So let's get started. So last week when we learned about how to find pH, I had told you guys in class that to find pH of weak acids or bases, you have to adopt a slightly different strategy. So here's a dissociation equation for hydrofluoric acid, which is HF. That is, when dissolved in water, gives you hydronium ion and the fluoride ion. Now, hydrofluoric acid, even though one of the most dangerous acid, is also a really weak acid. So if you think about what we had learned about the Lowry-Bronsted definition of acids and bases, according to that, this is an acid and this is a base. This is a conjugate acid and this is your conjugate base. You will also remember that the thing that makes hydrofluoric acid a weak acid is that this conjugate base is always going to get the H back from H3O. Okay? This conjugate base F negative is going to get the hydrogen atom back from H3O, which will favor the formation of your acid. So you cannot simply take the concentration of H3O based on the concentration of hydrofluoric acid that's given to you. Okay? So what I'm going to do is I'm going to explain this by taking an actual example. So let's see the process to find pH of a weak acid like hydrofluoric acid. So in this problem, they have given you a acetic acid solution whose molarity is known, and now you will see that there is an additional value provided to you, and that value is that of Ka. You will notice that this is the same Ka that we had learned in class, and that is called the equilibrium constant for weak acids. It's a weak acid because acetic acid does not dissociate completely. So let us set up the dissociation equation that we had learned in class. So what I want you to do is I will give you the left side of the equation and I want you to figure out the right side. So pause the video and figure it out. And here you go. So you have the acetate ion and the hydronium ion on the right side of the equation. Now, how can we use this equation to write down our equilibrium equation? So in the last set of notes that you took in class, I believe that was last week, Thursday, you should have the general equation for dissociation constant. So what I want you to do is use this, and this to write down your equilibrium equation. So go ahead and pause the video and hopefully you will get the same answer as I did. So the equation I got was Ka equals concentration of the hydronium ion times the concentration of the acetate ion divided by the concentration of the undissociated acetic acid. Now, when you look at this equation, you need to figure out what information do I know that is given in the problem and what information do I need to find. You will notice that this is given, right? So we'll put a check mark next to it. This is also given, so put a check mark next to that. Now, at this point, you have two variables that are unknown. You don't know the concentration of hydronium ion. You don't know the concentration of acetate ion. Now, the acetate ion is inconsequential. You do not need the acetate ion to find the pH, because if you remember, the equation for pH is negative log to to the base 10 of H plus ions, right? And at this point, let me clarify that H plus ions is basically the same as H3O positive. Okay, so when you see H positive, or if you see H3O positive, they are basically the same. They're exactly the same. So please don't get confused between H positive and H3O positive. They are used interchangeably. So, getting back to the problem, let's plug in the numbers that are given to us. And here's how my equation looks like. You will notice that I have two unknowns, my H3O positive, which is an unknown, and my CH3COO negative, which is also an unknown. And at this point, you need to understand something very, very important. And that part is that this concentration and this concentration are basically the same. What does that mean? It means that if the value of H3O positive is X, then the value of CH3COO negative is also X. Why is that? How can that be? I can rewrite this equation as 1.76 times 10 to the negative 5, which is the value of my equilibrium constant. And I will write H3O positive, but this time I'm going to write squared. I'm allowed to do that because I just explained this to you, that the concentrations of my hydronium ion is the same as the concentration of my acetate ion. And so whenever you write an equation that involves the dissociation constant, you will always end up with the squared of the hydronium ion. And obviously on the bottom, I still have my 0.7. Now essentially by doing this, what have you achieved? You have achieved yourself an equation with only one unknown, and that unknown is your concentration of H3O positive, which is eventually what you need to find your pH, right? Which is what you're ultimately after. So there's a lot to keep track of, but I promise you, once you do 3 or 4 problems on your own, you will get this down. It's not that hard. Now that you have this set up, what I'm going to do is, instead of writing H3O positive every time, I'm just going to write X. Okay, so X squared equals 0.7 times 1.76 times 10 to the negative 5, which gives me 1.2 times 10 to the negative 5. Now it's important that you remember that this is the value of X squared, which means if you want to find the value of X, you will have to take the square root of this number. So X would be equal to the square root of 1.2 times 10 to the negative 5. And that gives me 3.46 times 10 to the negative 3. What we just found is the concentration of H positive. All you need to do now is put this number in your pH equation. So pH would be negative log to the base 10 of 3.46 times 10 to the negative 3, and you will get your final answer. At this point, I am fairly positive that if you take these notes and when you come to class on Tuesday and you try to attempt some problems on your own without my help, you have a fairly good chance of getting these problems right. But if you watch this entire video and you have no clue as to how to do these, I'll be more than happy to help you one-on-one in class. But I won't do that until you have watched the video and you have taken notes over this, okay? So your number one priority is to watch the video and take notes, and I will see you in class. So let us look at the equation one more time. Let us consider that we started off this equation with 100 molecules of the undissociated acetic acid. Okay, now because this is a weak acid, let's make another assumption that maybe 5 molecules dissociated. Now, if 5 molecules dissociated, then I'm going to have 95 that are left over, right? Now, these 5 molecules that did dissociate, each molecule of CH3COOH is going to give me 1 molecule of H3O positive and 1 molecule of CH3COO negative. What do we take away from this? A very important point, which is that your concentration of H3O positive, which we represent by the brackets, is always going to be equal to the concentration of the anion, whatever that anion is. Okay, it could be acetate, it could be fluoride, it could be phosphate, it could be whatever, but their concentrations are always going to be the same. And so this is a very important factor, because now if we go back to the original equation we had set up,